So 109 is about finding the particular solution, 特解. Okay, and one of the main purpose of 109 is to say that you can use the RREF to determine whether a function, where an equation has a solution or not. Yeah. Okay. So here is some examples. Whenever we want to solve whenever we want to solve ax equal to b, say for example, we can do x1 plus x2 plus x3 plus x4 equal to 2. Let me write one equation. Okay, it's a lot of numbers, and we have 4 variables and 3 equations. And I believe all of you are able to solve this. You just kill some of the variables and you will solve this very quick. But just like what we did here, it's a lot of variables. We don't want to write the variable all the time. So we will write it as all the coefficients here. Okay, so this part is A. And there are some coefficient on the right-hand side. It is not part of the variable. It's a constant. We will draw a straight line and put 2, 3, 4 here. And this is B. And this structure is called augmented matrix, 增广矩阵. Augment means make it a bit bigger. If you see something like AR, it's anyway, AR, the A in AR is augmented or augmentation. I don't know, but augment means make it more, make it bigger. 增广实境嘛. Okay. So we use this augmented matrix to represent an equation, and it doesn't lose any information, right? It just missed the x1, x2, x3, and x4, and you know what are they. So an equation, a system of equation is the same as the augmented matrix. And if you just do this, apply the row echelon form, reduce row echelon form, then you will realize that you can use the first one to kill that, and then kill the last one too. Use the first row to kill the second row, it's 1, and then use the second row to kill the first row. Okay, so after some computation, it's not hard to get these things, and you feel like it should be fine. x1 plus x2 is equal to 1, x3 plus x4 is equal to 1. You can find a lot of solution from here, or just by setting the free variables as a parameter, then you can find a solution. But let's say we have the same A, but we choose a different B. And this time, let's try it with let's try it with 233. Okay, and then again you can do some reduced echelon form. Now you can use the first row to kill the second row, and then you realize, okay, it is the, you realize it is equal to 1. Use the first row to kill the third row. Here is also 1. Okay, but it will become something like this, and help me to double check whether it is correct. Okay, I believe it becomes 1, 1, and -1. Okay, I think that's right. So what happens here is what you learned before, the case of no solution, right? 无解. If you read this equation, it is fine. You read this equation, it is fine. But you read the last equation, then you realize that, okay, nothing, 0x1, 0x2, 0x3, 0x4, it is -1. And so this is impossible. Because of this rule, it says that no solution. And this one is fine. This has a solution. So the row reduced echelon form helps you to understand whether a system of linear equation has a solution or not. The criteria is the following. After you do the row echelon form, then if you see something that is 0 row, then the right hand side has to be 0. 0 row on the left, it will implies 0 entry, 0 constant. On the right. Otherwise, it is not solvable. You will find that there is no solution. Okay, so it's a simple idea, just telling you whether it has a solution or not. Right. But this is important. So let me emphasize a few things. Okay. Now you see this is AB, and this is A with another B. The first observation is when you do the row echelon form, it becomes like this and this. Although B is different, A is the same. So when you do the reduced echelon form, these two parts are the same, but the last column is different. Make sense? Right? So if you are solving an equation and the only different thing is on the right hand side, then the left hand side are always the same, right? You do the same reduction, same row operations to get the same thing. And secondly, why we care about having a solution or not? The other application of this is, recall that this one has a solution if and only if B is in the column space of A. So if we want to test whether B is in the column space or not, then we can simply solve the equation. This is probably 102 or 103. Your homework is like this. Okay, so we have the some of the equivalent condition or help you to test whether B is in the column space or not. So let me just copy some of the note. I'm a bit lazy now. So something here is from 109, and I'm just trying to copy two of the properties here. And then I guess this also means that you don't have to spend time to write it down. Okay, it has several conditions, but let's look at that one by one. Now you see, it says the following are equivalent. The following three statements, just the same way to describe the same behavior, different ways to describe the same behavior. So we know 1 and 3 are equivalent. Ax equal to b has a solution, then it means b is in the column space. And by solving x, you know how to write b as a linear combination of the columns. If you are not sure about this, then go back and check some of the previous lessons, and we have been talking about this. And now, has a solution or not? It has a solution or not can depends on the reduced echelon form. So we can write AB as an augmented matrix and run the reduced echelon form for that. And here it says that it does not contain a row where the let me just make a picture of this sentence. It is very long, but it says that this cannot happen. Okay, it cannot have a 0 contains a row. The last entry is 0. The last entry is non-zero. But all the other entries are 0. So this is not good. This implies no solution, as we have seen before. So if such a case does not happen, then we know that Ax equal to b has a solution. We are able to solve that, and these three statements are the same. It is simple, but you have to make a connection in your mind. If one day I ask you in the exam saying, can you test whether B, I give you A and B, can you tell me whether B is in the column space or not? Then you have to go back to solve the equation and tell me whether it has a solution or not. If it has a solution, then you know it is in the column space. Otherwise, it is no solution, then it is not in the column space. And how to tell that? You have to run the reduced echelon form and do this. But there is a special case. If all of these is okay, then there is a special case like this. In some special case, let's say R itself has no 0 row. Let's say we have A, B, and then you run the row operations to get a reduced echelon form and the new vector here. So by doing this, you know ax equal to b if and only if rx equal to r. This is just like a college way to write the same equation that you know before. Right? This is basically 加减消去法. Okay, now there is a special case example. Say we have a 1, 1, 1, 1, 2, 2. And now I don't really care what is B. Okay, I don't really care what is B. But notice that A is a little bit different. This entry is different. So after some row operations, then you are able to solve that. The reduced echelon form looks like this. And of course, the right-hand side also changes. But let's just write it as an R vector. And you will notice that in this spatial case, okay, I don't know what is B. But I know as long as I run the row reduced echelon form, the reduced echelon form has 3 non-zero entries, has 3 non-zero rows. So no matter what R is, it always has a solution. Okay? If R has the capital R has no 0 rows, then whatever the B or R you give me, I always can find a solution. So there is a special case that the reduced echelon form of A, the reduced echelon form of A contains no 0 row. And in this case, whatever the B you give me, Ax equal to B always has a solution for any B. And why we talk about this? Because this means that whatever the vector in B, whatever vector B in M, then it is going to be in the column space. Okay? Any vector in Rm is going to be in the vector space, in the column space. So this means your column space is the whole thing. Is the whole thing. For this case, the column space is equal to R3. So if one day I ask you that, okay, here is the matrix on the left-hand side, and can you tell me if the column space covers the whole space? You see the column, what is the column space? The column space is spanned by 1, 1, 1, 1, 1, 1, 2, 2, 1, 2, 3. And can you tell me if these 3 vectors span the whole space? Then answer is yes, because whatever the B in R3 you give me, then I can find the solution. So R3 is exactly equal to the column space. Questions? And a different way to say that is that if you look at the row echelon form, the reduced echelon form, then it has 3 pivots. 3 pivots, right? If it is m by n, then if you have m pivots, then that means you have m non-zero rows, and as long as you have m pivots, then this case happens. Okay, so I will leave a quick exercise for you to ponder, and you don't really have to calculate that, but you can think about it. If this is the question on the exam, or if this is the part of the problem for your research, or anytime you encounter this situation, and what you are going to do then. So A is equal to, this is called the Vandermonde matrix. It happens in some of the high school lectures, but it is not required to, it is, I guess it is not part of the lesson, but anyway, 就凡德梦矩阵. Okay, so is column space of A equal to R3?